Final project, building a multi-threaded web server. It's been a long journey, but we've reached the end of the book. In this chapter, we'll build one more project together to demonstrate some of the concepts we covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like Figure 21 in a web browser. Figure 21, our final shared project. Here is our plan for building the web server. Learn a bit about TCP and HTTP. Listen for TCP connections on a socket. Parse a small number of HTTP requests. Create a proper HTTP response. Improve the throughput of our server with a thread pool. Before we get started, we should mention one detail: the method we'll use won't be the best way to build a web server with Rust. Community members have published a number of production-ready crates available on crates.io that provide more complete web server and thread pool implementations than we'll build. However, our intention in this chapter is to help you learn, not to take the easy route. Because Rust is a systems programming language, we can choose the level of abstraction we want to work with and can go to a lower level than is possible or practical in other languages. We'll therefore write the basic HTTP server and thread pool manually so you can learn the general ideas and techniques behind the crates you might use in the future. Building a single-threaded web server. We'll start by getting a single-threaded web server working. Before we begin, let's look at a quick overview of the protocols involved in building web servers. The details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. The two main protocols involved in web servers are Hypertext Transfer Protocol, HTTP, and Transmission Control Protocol, TCP. Both protocols are request-response protocols, meaning a client initiates requests and a server listens to the requests and provides a response to the client. The contents of those requests and responses are defined by the protocols. TCP is the lower-level protocol that describes the details of how information gets from one server to another but doesn't specify what that information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in the vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and responses. Listening to the TCP connection. Our web server needs to listen to a TCP connection, so that's the first part we'll work on. The standard library offers std.net module that lets us do this. Let's make a new project in the usual fashion. Now enter the code in listing 2021 in src/main.rs to start. This code will listen at the local address 127.0.0.1:7878 for incoming TCP streams. When it gets an incoming stream, it will print connection established. File name src/main.rs. Listing 2021, listening for incoming streams and printing a message when we receive a stream. Using TCP Listener, we can listen for TCP connections at the address 127.0.0.1:7878. In the address, the section before the colon is an IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically, and 7878 is the port. We've chosen this port for two reasons. HTTP isn't normally accepted on this port, so our server is unlikely to conflict with any other web server you might have running on your machine, and 7878 is Rust typed on a telephone. The bind function in this scenario works like the new function in that it will return a new TCP listener instance. The function is called bind because, in networking, connecting to a port to listen to is known as binding to a port. The bind function returns a result TE, which indicates that it's possible for binding to fail. For example, connecting to port 80 requires administrator privileges. Non-administrators can listen only on ports higher than 1023, so if we tried to connect to port 80 without being an administrator, binding wouldn't work. Binding also wouldn't work, for example, if we ran two instances of our program and so had two programs listening to the same port. Because we're writing a basic server just for learning purposes, we won't worry about handling these kinds of errors. Instead, we use unwrap to stop the program if errors happen. The incoming method on TCP Listener returns an iterator that gives us a sequence of streams, more specifically, streams of type TCP stream. A single stream represents an open connection between the client and the server. A connection is the name for the full request and response process in which a client connects to the server generates a response, and the server closes the connection. As such, we will read from the TCP stream to see what the client sent and then write our response to the stream to send data back to the client. Overall, this for loop will process each connection in turn and produce a series of streams for us to handle. For now, our handling of the stream consists of calling unwrap to terminate our program if the stream has any errors. If there aren't any errors, the program prints a message. We'll add more functionality for the success case in the next listing. The reason we might receive errors from the incoming method when a client connects to the server is that we're not actually iterating over connections. Instead, we're iterating over connection attempts. The connection might not be successful for a number of reasons, many of them operating system specific. For example, many operating systems have a limit to the number of simultaneous open connections they can support. New connection attempts beyond that number will produce an error until some of the open connections are closed. Let's try running this code. Invoke cargo run in the terminal and then load 127.0.0.1:7878 in a web browser. The browser should show an error message like connection reset, because the server isn't currently sending back any data. But when you look at your terminal, you should see several messages that were printed when the browser connected to the server. Sometimes, you'll see multiple messages printed for one browser request. The reason might be that the browser is making a request for the page as well as a request for other resources, like the favicon.ico icon that appears in the browser tab. It could also be that the browser is trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by retrying, because the problem might be temporary. The important factor is that we've successfully gotten a handle to a TCP connection. Remember to stop the program by pressing Ctrl+C when you're done running a particular version of the code. Then restart the program by invoking the cargo run command after you've made each set of code changes to make sure you're running the newest code. Reading the request. Let's implement the functionality to read the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start a new function for processing connections. In this new handle_connection function, we'll read data from the TCP stream and print it so we can see the data being sent from the browser. Change the code to look like listing 20-2. File name src/main.rs. Listing 20-2, reading from the TCP stream and printing the data. We bring stdio prelude and stdio buffreader into scope to get access to traits and types that let us read from and write to the stream. In the for loop in the main function, instead of printing a message that says we made a connection, we now call the new handle_connection function and pass the stream to it. In the handle_connection function, we create a new buffreader instance that wraps immutable reference to the stream. Buffreader adds buffering by managing calls to the stdio read trait methods for us. We create a variable named http_request to collect the lines of the request the browser sends to our server. We indicate that we want to collect these lines in a vector by adding the vec_type annotation. Buffreader implements the stdio buffread trait, which provides the lines method. The lines method returns an iterator of result string, stdio error, by splitting the stream of data whenever it sees a new line byte. To get each string, we map and unwrap each result. The result might be an error if the data isn't valid UTF-8 or if there was a problem reading from the stream. Again, a production program should handle these errors more gracefully, but we're choosing to stop the program in the error case for simplicity. The browser signals the end of an HTTP request by sending 2 new line characters in a row, so to get one request from the stream, we take lines until we get a line that is the empty string. Once we've collected the lines into the vector, we're printing them out using pretty debug formatting so we can take a look at the instructions the web browser is sending to our server. Let's try this code. Start the program and make a request in a web browser again. Note that we'll still get an error page in the browser, but our program's output in the terminal will now look similar to this. Depending on your browser, you might get slightly different output. Now that we're printing the request data, we can see why we get multiple connections from one browser request by looking at the path after get in the first line of the request. If the repeated connections are all requesting /, we know the browser is trying to fetch / repeatedly because it's not getting a response from our program. Let's break down this request data to understand what the browser is asking of our program. A closer look at an HTTP request. HTTP is a text-based protocol, and a request takes this format. The first line is the request line that holds information about what the client is requesting. The first part of the request line indicates the method being used, such as GET or POST, which describes how the client is making this request. Our client used a GET request, which means it is asking for information. The next part of the request line is /, which indicates the Uniform Resource Identifier, URI, the client is requesting. A URI is almost, but not quite, the same as a Uniform Resource Locator, URL. The difference between URIs and URLs isn't important for our purposes in this chapter, but the HTTP spec uses the term URI, so we can just mentally substitute URL for URI here. The last part is the HTTP version the client uses, and then the request line ends in a CRLF sequence. CRLF stands for carriage return and line feed, which are terms from the typewriter days. The CRLF sequence can also be written as / or /n, where /r is a carriage return and /n is a line feed. The CRLF sequence separates the request line from the rest of the request data. Note that when the CRLF is printed, we see a new line start rather than / or /n. Looking at the request line data we received from running our program so far, we see that get is the method, / is the request URI, and HTTP /1.1 is the version. After the request line, the remaining lines starting from host onward are headers. GET requests have no body. Try making a request from a different browser or asking for a different address, such as 127.0.0.1:7878/test, to see how the request data changes. Now that we know what the browser is asking for, let's send back some data. Writing a response. We're going to implement sending data in response to a client request. Responses have the following format. The first line is a status line that contains the HTTP version used in the response, a numeric status code that summarizes the result of the request, and a reason phrase that provides a text description of the status code. After the CRLF sequence are any headers, another CRLF sequence, and the body of the response. Here is an example response that uses HTTP version 1.1, has a status code of 200, an OK reason phrase, no headers, and no body. The status code 200 is the standard success response. The text is a tiny successful HTTP response. Let's write this to the stream as our response to a successful request. From the handle_connection function, remove the println. That was printing the request data and replace it with the code in listing 20-3. File name src/main.rs. Listing 20-3, writing a tiny successful HTTP response to the stream. The first new line defines the response variable that holds the success message's data. Then we call as_bytes on our response to convert the string data to bytes. The write_all method on stream takes a and u8 and sends those bytes directly down the connection. Because the write_all operation could fail, we use unwrap on any error result as before. Again, in a real application you would add error handling here. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so we won't see any output other than the output from cargo. When you load 127.0.0.1:7878 in a web browser, you should get a blank page instead of an error. You've just hand-coded receiving an HTTP request and sending a response. Returning real HTML. Let's implement the functionality for returning more than a blank page. Create the new file hello.html in the root of your project directory, not in the src directory. You can input any HTML you want, listing 20-4 shows one possibility. File name, hello.html. Listing 20-4, a sample HTML file to return in a response. This is a minimal HTML5 document with a heading and some text. To return this from the server when a request is received, we'll modify handle_connection as shown in listing 20-5 to read the HTML file, add it to the response as a body, and send it. File name src/main.rs. Listing 20-5, sending the contents of hello.html as the body of the response. We've added fs to the use statement to bring the standard library's file system module into scope. The code for reading the contents of a file to a string should look familiar. We used it in Chapter 12 when we read the contents of a file for our I/O project in listing 12-4. Next, we use format to add the file's contents as the body of the success response. To ensure a valid HTTP response, we add the content length header, which is set to the size of our response body, in this case the size of hello.html. Run this code with cargo run and load 127.0.0.1:7878 in your browser. You should see your HTML rendered. Currently, we're ignoring the request data in HTTP_request and just sending back the contents of the HTML file unconditionally. That means if you try requesting 127.0.0.1:7878 something else in your browser, you'll still get back the same HTML response. At the moment, our server is very limited and does not do what most web servers do. We want to customize our responses depending on the request and only send back the HTML file for a well-formed request to /. Validating the request and selectively responding. Right now, our web server will return the HTML in the file no matter what the client requested. Let's add functionality to check that the browser is requesting / before returning the HTML file and return an error if the browser requests anything else. For this we need to modify handle_connection, as shown in listing 20-6. This new code checks the content of the request received against what we know a request for / looks like and adds if-and-else blocks to treat requests differently. File name src/main.rs. Listing 20-6, handling requests to / differently from other requests. We're only going to be looking at the first line of the HTTP request, so rather than reading the entire request into a vector, we're calling next to get the first item from the iterator. The first unwrap takes care of the option and stops the program if the iterator has no items. The second unwrap handles the result and has the same effect as the unwrap that was in the map added in listing 20-2. Next, we check the request_line to see if it equals the request line of a GET request to the / path. If it does, the if block returns the contents of our HTML file. If the request_line does not equal the GET request to the / path, it means we've received some other request. We'll add code to the else block in a moment to respond to all other requests. Run this code now and request 127.0.0.1:7878. You should get the HTML in hello.html. If you make any other request, such as 127.0.0.1:7878 / something else, you'll get a connection error like those you saw when running the code in listing 20-1 and listing 20-2. Now let's add the code in listing 20-7 to the else block to return a response with the status code 404, which signals that the content for the request was not found. We'll also return some HTML for a page to render in the browser indicating the response to the end user. File name src/main.rs. Listing 20-7, responding with status code 404 and an error page if anything other than / was requested. Here, our response has a status line with status code 404 and the reason phrase not found. The body of the response will be the HTML in the file 404.html. You'll need to create a 404.html file next to hello.html for the error page. Again, feel free to use any HTML you want or use the example HTML in listing 20-8. File name 404.html. Listing 20-8, sample content for the page to send back with any 404 response. With these changes, run your server again. Requesting 127.0.0.1:7878 should return the contents of hello.html, and any other request, like 127.0.0.1:7878 / foo, should return the error HTML from 404.html. A touch of refactoring. At the moment, the if-and-else blocks have a lot of repetition. They're both reading files and writing the contents of the files to the stream. The only differences are the status line and the file name. Let's make the code more concise by pulling out those differences into separate if-and-else lines that will assign the values of the status line and the file name to variables. We can then use those variables unconditionally in the code to read the file and write the response. Listing 20-9 shows the resulting code after replacing the large if-and-else blocks. File name src/main.rs. Listing 20-9, refactoring the if-and-else blocks to contain only the code that differs between the two cases. Now the if-and-else blocks only return the appropriate values for the status line and file name in a tuple. We then use destructuring to assign these two values to status_line and file name using a pattern in the let statement, as discussed in Chapter 18. The previously duplicated code is now outside the if-and-else blocks and uses the status_line and file name variables. This makes it easier to see the difference between the two cases, and it means we have only one place to update the code if we want to change how the file reading and response writing work. The behavior of the code in listing 20-9 will be the same as that in listing 20-8. Awesome! We now have a simple web server and approximately 40 lines of Rust code that responds to one request with a page of content and responds to all other requests with a 404 response. Currently, our server runs in a single thread, meaning it can only serve one request at a time. Let's examine how that can be a problem by simulating some slow requests. Then we'll fix it so our server can handle multiple requests at once, turning our single-threaded server into a multi-threaded server. Right now, the server will process each request in turn, meaning it won't process a second connection until the first is finished processing. If the server received more and more requests, this serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new requests can be processed quickly. We'll need to fix this, but first, we'll look at the problem in action. Simulating a slow request in the current server implementation. Well, look at how a slow processing request can affect other requests made to our current server implementation. Listing 20 to 10 implements handling a request to /sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. File name src/main.rs. Listing 20 to 10, simulating a slow request by sleeping for 5 seconds. We switched from if to match now that we have 3 cases. We need to explicitly match on a slice of request_line to pattern match against the string literal values. Match doesn't do automatic referencing and dereferencing like the equality method does. The first arm is the same as the if block from listing 20 to 9. The second arm matches a request to /sleep. When that request is received, the server will sleep for 5 seconds before rendering the successful HTML page. The third arm is the same as the else block from listing 20 to 9. You can see how primitive our server's real libraries would handle the recognition of multiple requests in a much less verbose way. Start the server using cargo run. Then open 2 browser windows, one for http://127.0.0.1:7878/ and the other for http://127.0.0.1:7878/sleep. If you enter the /URI a few times, as before, you'll see it respond quickly. But if you enter /sleep and then load /, you'll see that / waits until sleep has slept for its full 5 seconds before loading. There are multiple techniques we could use to avoid requests backing up behind a slow request. The one we'll implement is a thread pool. Improving throughput with a thread pool. A thread pool is a group of spawn threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool to the task, and that thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processing. When the first thread is done processing its task, it's returned to the pool of idle threads, ready to handle a new task. A thread pool allows you to process connections concurrently, increasing the throughput of your server. We'll limit the number of threads in the pool to a small number to protect us from denial of service, DOS, attacks. If we had our program create a new thread for each request as it came in, someone making 10 million requests to our server could create havoc by using up all our server's resources and grinding the processing of requests to a halt. Rather than spawning unlimited threads, then, we'll have a fixed number of threads waiting in the pool. Requests that come in are sent to the pool for processing. The pool will maintain a queue of incoming requests. Each of the threads in the pool will pop off a request from this queue, handle the request, and then ask the queue for another request. With this design, we can process up to n requests concurrently, where n is the number of threads. If each thread is responding to a long-running request, subsequent requests can still back up in the queue, but we've increased the number of long-running requests we can handle before reaching that point. This technique is just one of many ways to improve the throughput of a web server. Other options you might explore are the fork/join model, the single-threaded async I/O model, or the multi-threaded async I/O model. If you're interested in this topic, you can read more about other solutions and try to implement them with a low-level language like Rust. All of these options are possible. Before we begin implementing a thread pool, let's talk about what using the pool should look like. When you're trying to design code, writing the client interface first can help guide your design. Write the API of the code so it's structured in the way you want to call it, then implement the functionality within that structure rather than implementing the functionality and then designing the public API. Similar to how we used test-driven development in the project in Chapter 12, we'll use compiler-driven development here. We'll write the code that calls the functions we want, and then we'll look at errors from the compiler to determine what we should change next to get the code to work. Before we do that, however, we'll explore the technique we're not going to use as a starting point. Spawning a thread for each request. First, let's explore how our code might look if it did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point to get a working multi-threaded server first. Then we'll add the thread pool as an improvement, and contrasting the two solutions will be easier. Listing 20 to 11 shows the changes to make to main to spawn a new thread to handle each stream within the for loop. File name src/main.rs. Listing 20 to 11, spawning a new thread for each stream. As you learned in Chapter 16, thread spawn will create a new thread and then run the code in the closure in the new thread. If you run this code and load /sleep in your browser, then / in 2 more browser tabs, you'll indeed see that the requests to / don't have to wait for /sleep to finish. However, as we mentioned, this will eventually overwhelm the system because you'd be making new threads without any limit. Creating a finite number of threads. We want our thread pool to work in a similar, familiar way, so switching from threads to a thread pool doesn't require large changes to the code that uses our API. Listing 20 to 12 shows the hypothetical interface for a thread pool struct we want to use instead of thread spawn. File name src/main.rs. Listing 20 to 12, our ideal thread pool interface. We use thread pool new to create a new thread pool with a configurable number of threads, in this case 4. Then, in the for loop, pool.execute has a similar interface as thread spawn in that it takes a closure the pool should run for each stream. We need to implement pool.execute so it takes the closure and gives it to a thread in the pool to run. This code won't yet compile, but we'll try so the compiler can guide us in how to fix it. Building thread pool using compiler-driven development. Make the changes in listing 20 to 12 to src/main.rs, and then let's use the compiler errors from cargo check to drive our development. Here is the first error we get. Great! This error tells us we need a thread pool type or module, so we'll build one now. Our thread pool implementation will be independent of the kind of work our web server is doing. So, let's switch the hello crate from a binary crate to a library crate to hold our thread pool implementation. After we change to a library crate, we could also use the separate thread pool library for any work we want to do using a thread pool, not just for serving web requests. Create a src/librs that contains the following, which is the simplest definition of a thread pool struct that we can have for now. File name src/librs. Then edit main.rs file to bring thread pool into scope from the library crate by adding the following code to the top of src/main.rs. File name src/main.rs. This code still won't work, but let's check it again to get the next error that we need to address. This error indicates that next we need to create an associated function named new for thread pool. We also know that new needs to have one parameter that can accept 4 as an argument and should return a thread pool instance. Let's implement the simplest new function that will have those characteristics. File name src/librs. We chose usize as the type of the size parameter, because we know that a negative number of threads doesn't make any sense. We also know we'll use this for as the number of elements in a collection of threads, which is what the usize type is for, as discussed in the integer types section of chapter 3. Let's check the code again. Now the error occurs because we don't have an execute method on thread pool. Recall from the creating a finite number of threads section that we decided our thread pool should have an interface similar to thread spawn. In addition, we'll implement the execute function so it takes the closure it's given and gives it to an idle thread in the pool to run. We'll define the execute method on thread pool to take a closure as a parameter. Recall from the moving captured values out of the closure and the fn traits section in chapter 13 that we can take closures as parameters with 3 different traits, fn, fnmut, and fn_once. We need to decide which kind of closure to use here. We know we'll end up doing something similar to the standard library thread spawn implementation, so we can look at what bounds the signature of thread spawn has on its parameter. The documentation shows us the following. The f-type parameter is the one we're concerned with here, the t-type parameter is related to the return value, and we're not concerned with that. We can see that spawn uses fn_once as the trait bound on f. This is probably what we want as well, because we'll eventually pass the argument we get in execute to spawn. We can be further confident that fn_once is the trait we want to use because the thread for running a request will only execute that request's closure one time, which matches the once in fn_once. The f-type parameter also has the trait bound send and the lifetime bound static, which are useful in our situation. We need send to transfer the closure from one thread to another and static because we don't know how long the thread will take to execute. Let's create an execute method on thread pool that will take a generic parameter of type f with these bounds. File name src/librs. We still use the after fn_once because this fn_once represents a closure that takes no parameters and returns the unit type. Just like function definitions, the return type can be omitted from the signature, but even if we have no parameters, we still need the parentheses. Again, this is the simplest implementation of the execute method. It does nothing, but we're trying only to make our code compile. Let's check it again. It compiles. But note that if you try cargo run and make a request in the browser, you'll see the errors in the browser that we saw at the beginning of the chapter. Our library isn't actually calling the closure pass to execute yet. Validating the number of threads in new. We aren't doing anything with the parameters to new and execute. Let's implement the bodies of these functions with the behavior we want. To start, let's think about new. Earlier we chose an unsigned type for the size parameter, because a pool with a negative number of threads makes no sense. However, a pool with 0 threads also makes no sense, yet 0 is a perfectly valid usize. We'll add code to check that size is greater than 0 before we return a thread pool instance and have the program panic if it receives a 0 by using the assert macro, as shown in listing 20 to 13. Filename src/librs. Listing 20 to 13, implementing thread pool new to panic if size is 0. We've also added some documentation for our thread pool with doc comments. Note that we followed good documentation practices by adding a section that calls out the situations in which our function can panic, as discussed in Chapter 14. Try running cargo doc open and clicking the thread pool struct to see what the generated docs for new look like. Instead of adding the assert macro as we've done here, we could change new into build and return a result like we did with config build in the IO project in listing 12 to 9. But we've decided in this case that trying to create a thread pool without any threads should be an unrecoverable error. If you're feeling ambitious, try to write a function named build with the following signature to compare with the new function. Creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them in the thread pool struct before returning the struct. But how do we store a thread? Let's take another look at the thread spawn signature. The spawn function returns a join handle t, where t is the type that the closure returns. Let's try using join handle 2 and see what happens. In our case, the closures we're passing to the thread pool will handle the connection and not return anything, so t will be the unit type. The code in listing 20 to 14 will compile but doesn't create any threads yet. We've changed the definition of thread pool to hold a vector of thread join handle instances, initialized the vector with a capacity of size, set up a for loop that will run some code to create the threads, and returned a thread pool instance containing them. Filename src/librs. Listing 20 to 14, creating a vector for thread pool to hold the threads. We've brought std thread into scope in the library crate, because we're using thread join handle as the type of the items in the vector in thread pool. Once a valid size is received, our thread pool creates a new vector that can hold size items. The with_capacity function performs the same task as vec_new but with an important difference: it pre-allocates space in the vector. Because we know we need to store size elements in the vector, doing this allocation up front is slightly more efficient than using vec_new, which resizes itself as elements are inserted. When you run cargo check again, it should succeed. A worker struct responsible for sending code from the thread pool to a thread. We left a comment in the for loop in listing 20 to 14 regarding the creation of threads. Here, we'll look at how we actually create threads. The standard library provides thread spawn as a way to create threads, and thread spawn expects to get some code the thread should run as soon as the thread is created. However, in our case, we want to create the threads and have them wait for code that we'll send later. The standard library's implementation of threads doesn't include any way to do that, we have to implement it manually. We'll implement this behavior by introducing a new data structure between the thread pool and the threads that will manage this new behavior. We'll call this data structure worker, which is a common term in pooling implementations. The worker picks up code that needs to be run and runs the code in the worker's thread. Think of people working in the kitchen at a restaurant. The workers wait until orders come in from customers, and then they're responsible for taking those orders and fulfilling them. Instead of storing a vector of join handle instances in the thread pool, we'll store instances of the worker struct. Each worker will store a single join handle instance. Then we'll implement a method on worker that will take a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID so we can distinguish between the different workers in the pool when logging or debugging. Here is the new process that will happen when we create a thread pool. We'll implement the code that sends the closure to the thread after we have worker set up in this way. Define a worker struct that holds an ID and a join handle. Change thread pool to hold a vector of worker instances. Define a worker new function that takes an ID number and returns a worker instance that holds the ID and a thread spawned with an empty closure. In thread pool new, use the for loop counter to generate an ID, create a new worker with that ID, and store the worker in the vector. If you're up for a challenge, try implementing these changes on your own before looking at the code in listing 20 to 15. Ready? Here is listing 20 to 15 with one way to make the preceding modifications. Filename src/librs. Listing 20 to 15, modifying thread pool to hold worker instances instead of holding threads directly. We've changed the name of the field on thread pool from threads to workers because it's now holding worker instances instead of join handle instances. We use the counter in the for loop as an argument to worker new, and we store each new worker in the vector named workers. External code, like our server in src/main.rs, doesn't need to know the implementation details regarding using a worker struct within thread pool, so we make the worker struct and its new function private. The worker new function uses the ID we give it and stores a join handle instance that is created by spawning a new thread using an empty closure. This code will compile and will store the number of worker instances we specified as an argument to thread pool new. But we're still not processing the closure that we get in execute. Let's look at how to do that next. Sending requests to threads via channels. The next problem we'll tackle is that the closures given to thread spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method. But we need to give thread spawn a closure to run when we create each worker during the creation of the thread pool. We want the worker structs that we just created to fetch the code to run from a queue held in the thread pool and send that code to its thread to run. The channels we learned about in Chapter 16, a simple way to communicate between two threads, would be perfect for this use case. We'll use a channel to function as the queue of jobs, and execute will send a job from the thread pool to the worker instances, which will send the job to its thread. Here is the plan. The thread pool will create a channel and hold on to the sender. Each worker will hold on to the receiver. We'll create a new job struct that will hold the closures we want to send down the channel. The execute method will send the job it wants to execute through the sender. In its thread, the worker will loop over its receiver and execute the closures of any jobs it receives. Let's start by creating a channel in thread pool new and holding the sender in the thread pool instance, as shown in listing 20 to 16. The job struct doesn't hold anything for now, but will be the type of item we're sending down the channel. File name src/librs. Listing 20 to 16, modifying thread pool to store the sender of a channel that transmits job instances. In thread pool new, we create our new channel and have the pool hold the sender. This will successfully compile. Let's try passing a receiver of the channel into each worker as the thread pool creates the channel. We know we want to use the receiver in the thread that the workers spawn, so we'll reference the receiver parameter in the closure. The code in listing 20 to 17 won't quite compile yet. File name src/librs. Listing 20 to 17, passing the receiver to the workers. We've made some small and straightforward changes. We pass the receiver into worker new, and then we use it inside the closure. When we try to check this code, we get this error. The code is trying to pass receiver to multiple worker instances. This won't work. As you'll recall from Chapter 16, the channel implementation that Rust provides is multiple producer, single consumer. This means we can't just clone the consuming end of the channel to fix this code. We also don't want to send a message multiple times to multiple consumers. We want one list of messages with multiple workers such that each message gets processed once. Additionally, taking a job off the channel queue involves mutating the receiver, so the threads need a safe way to share and modify receiver, otherwise, we might get race conditions, as covered in Chapter 16. Recall the thread-safe smart pointers discussed in Chapter 16. To share ownership across multiple threads and allow the threads to mutate the value, we need to use arg_mutex_t. The arg type will let multiple workers own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. Listing 20 to 18 shows the changes we need to make. File name src/librs. Listing 20 to 18, sharing the receiver among the workers using arg and mutex. In thread pool new, we put the receiver in an arg and a mutex. For each new worker, we clone the arg to bump the reference count so the workers can share ownership of the receiver. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on thread pool. We'll also change job from a struct to a type alias for a trait object that holds the type of closure that execute receives. As discussed in the Creating Type Synonyms with Type Aliases section of Chapter 19, type aliases allow us to make long types shorter for ease of use. Look at listing 20 to 19. File name src/librs. Listing 20 to 19, creating a job type alias for a box that holds each closure and then sending the job down the channel. After creating a new job instance using the closure we get in execute, we send that job down the sending end of the channel. We're calling unwrap on send for the case that sending fails. This might happen if, for example, we stop all our threads from executing, meaning the receiving end has stopped receiving new messages. At the moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. But we're not quite done yet. In the worker, our closure being passed to thread spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets one. Let's make the change shown in listing 20 to 20 to worker new. File name src/librs. Listing 20 to 20, receiving and executing the jobs in the worker's thread. Here, we first call lock on the receiver to acquire the mutex, and then we call unwrap to panic on any errors. Acquiring a lock might fail if the mutex is in a poisoned state, which can happen if some other thread panicked while holding the lock rather than releasing the lock. In this situation, calling unwrap to have this thread panic is the correct action to take. Feel free to change this unwrap to an expect with an error message that is meaningful to you. If we get the lock on the mutex, we call rec to receive a job from the channel. A final unwrap moves past any errors here as well, which might occur if the thread holding the sender has shut down, similar to how the send method returns error if the receiver shuts down. The call to rec blocks, so if there is no job yet, the current thread will wait until a job becomes available. The mutex T ensures that only one worker thread at a time is trying to request a job. Our thread pool is now in a working state. Give it a cargo run and make some requests. Success! We now have a thread pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make a request to /sleep, the server will be able to serve other requests by having another thread run them. After learning about the while-let loop in Chapter 18, you might be wondering why we didn't write the worker thread code as shown in listing 20 to 21. File name src/librs. Listing 20 to 21, an alternative implementation of worker new using while-let. This code compiles and runs but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait to be processed. The reason is somewhat subtle. The mutex struct has no public unlock method because the ownership of the lock is based on the lifetime of the mutex guard T within the lock result mutex guard T that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by a mutex cannot be accessed unless we hold the lock. However, this implementation can also result in the lock being held longer than intended if we aren't mindful of the lifetime of the mutex guard T. The code in listing 20 to 20 that uses let job equals receiver.lock.unwrap.rec.unwrap works because with let, any temporary values used in the expression on the right-hand side of the equals sign are immediately dropped when the let statement ends. However, while let, and if let and match, does not drop temporary values until the end of the associated block. In listing 20 to 21, the lock remains held for the duration of the call to job, meaning other workers cannot receive jobs. Graceful shutdown and cleanup. The code in listing 20 to 20 is responding to requests asynchronously through the use of a thread pool, as we intended. We get some warnings about the worker's ID and thread fields that we're not using in a direct way that reminds us we're not cleaning up anything. When we use the less elegant Control-C method to halt the main thread, all other threads are stopped immediately as well, even if they're in the middle of serving a request. Next, then, we'll implement the drop trait to call join on each of the threads in the pool so they can finish the requests they're working on before closing. Then we'll implement a way to tell the threads they should stop accepting new requests and shut down. To see this code in action, we'll modify our server to accept only 2 requests before gracefully shutting down its thread pool. Implementing the drop trait on thread pool. Let's start with implementing drop on our thread pool. When the pool is dropped, our threads should all join to make sure they finish their work. Listing 20 to 22 shows a first attempt at a drop implementation. This code won't quite work yet. File name src/librs. Listing 20 to 22, joining each thread when the thread pool goes out of scope. First, we loop through each of the thread pool workers. We use mut for this because self is a mutable reference, and we also need to be able to mutate worker. For each worker, we print a message saying that this particular worker is shutting down, and then we call join on that worker's thread. If the call to join fails, we use unwrap to make Rust panic and go into an ungraceful shutdown. Here is the error we get when we compile this code. The error tells us we can't call join because we only have a mutable borrow of each worker and join takes ownership of its argument. To solve this issue, we need to move the thread out of the worker instance that owns thread so join can consume the thread. We did this in listing 17 to 15. If worker holds an option thread join handle, instead, we can call the take method on the option to move the value out of the some variant and leave a none variant in its place. In other words, a worker that is running will have a some variant in thread, and when we want to clean up a worker, we'll replace some with none so the worker doesn't have a thread to run. So we know we want to update the definition of worker like this. Filename src/librs. Now let's lean on the compiler to find the other places that need to change. Checking this code, we get 2 errors. Let's address the second error, which points to the code at the end of worker new. We need to wrap the thread value in some when we create a new worker. Make the following changes to fix this error. Filename src/librs. The first error is in our drop implementation. We mentioned earlier that we intended to call take on the option value to move thread out of worker. The following changes will do so. Filename src/librs. As discussed in Chapter 17, the take method on option takes the sum variant out and leaves none in its place. We're using iflet to destructure the sum and get the thread, then we call join on the thread. If a worker's thread is already none, we know that worker has already had its thread cleaned up, so nothing happens in that case. Signaling to the threads to stop listening for jobs. With all the changes we've made, our code compiles without any warnings. However, the bad news is this code doesn't function the way we want it to yet. The key is the logic in the closures run by the threads of the worker instances. At the moment, we call join, but that won't shut down the threads because they loop forever looking for jobs. If we try to drop our thread pool with our current implementation of drop, the main thread will block forever waiting for the first thread to finish. To fix this problem, we'll need a change in the thread pool drop implementation and then a change in the worker loop. First, we'll change the thread pool drop implementation to explicitly drop the sender before waiting for the threads to finish. Listing 20 to 23 shows the changes to thread pool to explicitly drop sender. We use the same option and take technique as we did with the thread to be able to move sender out of thread pool. Filename src/librs. Listing 20 to 23 explicitly drops sender before joining the worker threads. Dropping sender closes the channel, which indicates no more messages will be sent. When that happens, all the calls to rect that the workers do in the infinite loop will return an error. In listing 20 to 24, we change the worker loop to gracefully exit the loop in that case, which means the threads will finish when the thread pool drop implementation calls join on them. Filename src/librs. Listing 20 to 24 explicitly break out of the loop when rect returns an error. To see this code in action, let's modify main to accept only 2 requests before gracefully shutting down the server, as shown in listing 20 to 25. Filename src/main.rs. Listing 20 to 25, shut down the server after serving 2 requests by exiting the loop. You wouldn't want a real-world web server to shut down after serving only 2 requests. This code just demonstrates that the graceful shutdown and cleanup is in working order. The take method is defined in the iterator trait and limits the iteration to the first 2 items at most. The thread pool will go out of scope at the end of main, and the drop implementation will run. Start the server with cargo run, and make 3 requests. The third request should error, and in your terminal you should see output similar to this. You might see a different ordering of workers and messages printed. We can see how this code works from the messages. Workers 0 and 3 got the first 2 requests. The server stopped accepting connections after the second connection, and the drop implementation on thread pool starts executing before worker 3 even starts its job. Dropping the sender disconnects all the workers and tells them to shut down. The workers each print a message when they disconnect, and then the thread pool calls join to wait for each worker thread to finish. Notice one interesting aspect of this particular execution: the thread pool dropped the sender, and before any worker received an error, we tried to join worker 0. Worker 0 had not yet gotten an error from rec, so the main thread blocked waiting for worker 0 to finish. In the meantime, worker 3 received a job and then all threads received an error. When worker 0 finished, the main thread waited for the rest of the workers to finish. At that point, they had all exited their loops and stopped. Congrats! We've now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all the threads in the pool. Hey, race the full code for reference. Filename src/main.rs. Filename src/librs. We could do more here. If you want to continue enhancing this project, here are some ideas. Add more documentation to thread pool and its public methods. Add tests of the library's functionality. Change calls to unwrap to more robust error handling. Use thread pool to perform some task other than serving web requests. Find a thread pool crate on crates.io and implement a similar web server using the crate instead. Then compare its API and robustness to the thread pool we implemented. Summary. Well done. You've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You're now ready to implement your own Rust projects and help with other people's projects. Keep in mind that there is a welcoming community of other Rustaceans who would love to help you with any challenges you encounter on your Rust journey.